Welcome everyone. Today we're very happy to have Carlos Arguelles, who's virtually visiting us from the Harvard Physics Department, where he joined the faculty last year. Carlos did his undergrad at the Pontificia Católica University in Peru, in Lima, where he's from. And after spending time in his master's at Fermilab, he moved to University of Wisconsin-Madison for his PhD. He joined IceCube and he did a postdoc at the Wisconsin IceCube Particle Astrophysics Center, and then at MIT before joining Harvard. Carlos's research spans theory and experiment in a way that I find really interesting because he's both a key member of the IceCube collaboration and he leads the Beyond Standard Model Physics group, but he's written pioneering theory papers on things like neutrinos, like light-scale neutrinos, or neutrino flavor anomalies and things like that. And I really enjoyed reading those papers. Carlos won many awards. Most recently, Carlos was selected a 2021 Sloan Fellow, which is a huge honor, one of the highest for like a young astrophysicist. And not only is Carlos a rising star in astrophysics, he's also an LGBTQ+ scientist who's interested in promoting an inclusive environment in astrophysics. Carlos told me he's very keen on collaborating with people at the CFA. So I really look forward to what he's going to tell us today. And before handing it to Carlos, let me remind all of you to please mute yourselves if you don't actually want to speak so we can minimize the sneaker-related noise. So please, Carlos, take it away.
For a very nice introduction. And yeah, I just want to echo again the words that I'm very interested in collaborating and chatting with people. So please feel free to contact me after the talk and if you want to keep chatting. So today I'm going to talk about high energy neutrino astroparticle physics with IceCube. Oops, hold on a second, let me see. Yeah, sorry. So what are the questions that I'm interested here? There's essentially two questions. One of them is, how does the universe look in neutrinos? And of course, we have seen the universe in many ways, and you are all experts on that. We have seen it with photons at different wavelengths. In particular for this talk, it's going to be relevant, the observation of gamma rays. And here I show you some Cherenkov telescopes and Fermi in the right panel. We now are able to also see the universe or hear it in some fashion using gravitational waves. And neutrinos are going to be a complementary window to observing the universe. Particle physics is by formation. And one of the questions I really want to think about is if the observation of high neutrinos produced out there, if those neutrinos do what we expect them to do in the standard model or not. And so I think these questions are correlated. I'm going to give you an example of why I think they're correlated. So this is a picture of the sun in neutrinos taken by Super Kamiokande in 1998. And I think this exemplifies what I was saying earlier very nicely. And the reason is that when we saw neutrinos from the sun, back in the day from like Davis experiments, though they didn't have any pointing, but we knew were solar neutrinos, there was a big discrepancy between the theoretical expectations of the rate at which we see neutrinos from the sun and the actual solar neutrinos that we observed. It took a long time to understand that discrepancy. I want to say maybe 30 or 40 years. And eventually it turns out that we actually learned a lot about neutrinos. We learned that neutrinos, in fact, are able to change between flavors. I'm going to talk about that more in some minutes. And we also got to understand a little more about how the inner workings of the sun. So this is sort of what I'm trying to do in my research, is to learn about the sources and also learn about neutrinos, and I hope to find surprises. And so why do I say that I hope to find surprises? First of all, let me say that the model that I'm basing my work is the standard model, and the standard model is a truly successful model. It's very predictive. It has 18 parameters, and it has an amazing agreement in observable after observable. However, the standard model is for a fundamental theory, and it's, in my opinion, a quite complicated theory. Here you see all of the standard model particle contents separated by quarks, leptons, and antiquarks, antileptons, as well as the mediators. And so the standard model is arranged in rows and columns that have a particular pattern. Some of this pattern is actually not explained in a fundamental way. For example, the flavor structure standard model does not come out of the box. So it's rather complicated. This is not something new. We have seen in the past complicated patterns that turn out to have a deeper underlying explanation. So here, it's now a couple of years from now, but a couple of years ago, it was the 100th anniversary of the periodic table. And in the periodic table, we arrange elements by common features. And similarly, we found out that the elements had common features because they had similar electromagnetic properties. And so that was able to be understood once we knew quantum mechanics to be able to understand this problem. So my hope is that something similar will happen with the standard model. I also think that there should be, we also know there should be something beyond the standard model, because the standard model is not able to predict the particle content of the universe. Today, only about 5% of the universe is formed from what we call standard model particles. Finally, and importantly for this talk, the standard model has so far yielded surprises in the neutrino sector. As I was mentioning earlier, the fact that neutrinos change flavors when they're going from the sun to us implies that neutrinos have non-zero mass, which is something that was not originally predicted by standard model, and we don't have a good explanation for that. So there is something out there to learn, and the question is how we're going to learn about it. So with that stage, I'm going to outline the rest of my talk. So I'm going to talk about neutrinos in general, just a nutshell of what they are. Then I'm going to talk about neutrinos as cosmic messengers and IceCube. And then I'm going to tell you 3 ways in which IceCube finds astrophysical neutrinos. And then I'm going to give you 2 examples of how we can use astrophysical neutrinos to do particle physics. And then I'm going to talk a little about the future. So let me talk about neutrinos in general. So there are 3 light neutrinos. The neutrinos are actually very light, but non-zero in mass. The neutrinos are actually coming from everywhere right now. To one of your thumbnails, there are more than 40 billion neutrinos going through. And neutrinos can have both natural origin or anthropogenic origin. For example, natural neutrino sources are the sun, which I showed you earlier. There are neutrinos from supernova, which we have seen more than 30 years ago. There are also relic neutrinos from the Big Bang, which we have not seen. There are going to be neutrinos that are produced by cosmic ray air showers. And I'm going to talk more about those neutrinos later in my talk. There are also neutrinos produced by people, and those are anthropogenic neutrino sources. And in that category, you can find reactor neutrinos or neutrinos producing accelerators. Neutrinos only interact via the weak force, which means that their interactions are going to be rare. For example, a solar neutrino has a cross-section against a proton of about 10 to the minus 43 centimeters squared. And if you compare that to the typical proton-proton cross-section, that's actually 10 to the 20 times larger. And that means that a low-energy neutrino can travel about 200 Earths before interacting at all. And that's going to be true for low-energy neutrinos. However, at higher energies, that will be different. So just to put the stage together, when we talk about interactions in particle physics, we organize them or depict them in these Feynman diagrams. So the horizontal axis is time and the vertical axis is position. So the weak interaction can be explained as an exchange of particles. In this case, this looks like a normal scatter. You have a neutrino, it hits a d quark, and out comes a neutrino and a d quark. This kind of process we call a neutral current exchange. The neutrinos have another kind of interaction, which is called a charge current exchange. And this interaction is actually going to change the nature of the neutrino. In this case, you're going to have a neutrino come along, interact with a quark, and then out it comes not a neutrino, but an electron. We're going to then label the neutrinos according to the outgoing particles of the charge interaction. So an electron neutrino is a neutrino that when it has a charge current interaction produces an electron, a mu neutrino, similarly mu and a neutrino at tau. In the standard model, neutrinos and their charge partners, as we call them, are intimately related. Oops. Neutrinos are neutral particles. So how do we see them? We can only see charged particles in our detectors. So the neutrino is going to be invisible, but it's going to interact. It's going to make a harmonic shower or produce an electron or a muon, depending on the type of neutrino. And those charged particles are going to emit different types of light. They could ionize materials, they could produce scintillation light, and importantly for us, they could produce Cherenkov radiation. So this is an example in the right of how a Cherenkov cone that's produced by a mu neutrino looks in a typical neutrino experiment. IceCube is an experiment that operates by observing the Cherenkov light produced by charged particles. So now let me tell you a little more about something that I mentioned earlier, which is that neutrinos can change flavor. So how does that work? So you start with a given neutrino source. So look at the in the bottom. The pink color is the mu neutrino. So my initial source of neutrinos contains only mu neutrinos. Some distance further away from my source, I measure my neutrino content, and I see that part of my neutrinos are going to be still mu neutrinos, but some of them have shifted to become electron neutrinos. And then I move further along, and I measure again, and I get again mu neutrinos. And this goes on and on and on, where the neutrinos go from mu to electron, mu to electron, mu to electrons. That periodic behavior implies that the neutrinos have, in some sense, a sense of time that they know how to switch between one flavor and another. The formula on the top tells you how does the neutrino oscillation probability is going to depend on the neutrino parameters, which in this case is going to be the mass difference between the neutrino mass states. So we understand, or we think we understand why this happens. It happens because the neutrinos have mass, and the mass states and the flavor states are not quite aligned. And we have performed various experimental measurements to try to measure the parameters that dictate the Hamiltonian that you see there that governs this phenomena. Okay, so that's what I want to tell you about neutrinos, essentially that they interact weakly. They are ubiquitous, they produce all over the place, and they can change flavors. Now I want to talk about neutrinos as cosmic messengers and how do we see neutrinos in IceCube. So one of the, maybe the oldest problem in astroparticle physics is the origin of cosmic rays. And here you have seen the cosmic ray spectrum that spans many decades in energy and in intensity. And so the challenge here is to find what is the origin of these cosmic rays. And this is difficult because we need to have accelerators that produce high luminosity and large energy. So how can we accelerate particles? So we know how to do that at Earth. So at Earth, we accelerate particles, for example, at the LHC, where we can produce high energy, high luminosity particles. The highest energy cosmic ray was seen by Flyer in 1991. And if we would like to accelerate a proton to the comparable energy of that cosmic ray, we need to build an LHC-like accelerator that is roughly 10 to the 20 times, it's roughly the size of Mercury. Okay, so the universe has accelerators, much like we have accelerators here on Earth. So those accelerators are going to produce beams of particles in both heaven and Earth. So you're going to have an accelerator, which could be, for example, a supermassive black hole. It's going to accelerate particles. Then there's going to be a target material. It's going to be, in this case, could be, for example, radiation or dust around the accelerator region. Then the accelerated particle, for example, the proton, is the target material, and then that produces a beam of particles. The beam of particles is going to yield as neutrinos. So for example, you can have a proton interacting with radiation, producing a neutron and a charged pion. That charged pion will give you a neutrino. Naively, we expect that we will also get a neutral pion production, and the neutral pion production is going to be associated with gamma rays. So we could study the universe or this accelerator with gamma rays. However, there is a difficulty with that. And the difficulty is that the universe is opaque to high energy gamma rays. So you have your accelerator, and if you have a very high energy gamma ray produced from it, that gamma ray can then produce a pair of electrons as it interacts with the CMB on the way to the Earth. Protons, on the other hand, protons also do not do that. However, they get deflected by magnetic fields, or get deflected by magnetic fields on their way to the Earth from us. So that's enter the neutrino. The neutrino is going to be part of the highest energy radiation of the universe, and it's going to allow us to see a part of the universe that we cannot see without them. So here you can see the energy of the messenger on the horizontal axis, and then the distance that the universe is transparent. You can see that high energy, somewhere around 100 TeVs, the universe becomes opaque, and that regime can be resolved with neutrinos, cosmic rays, and positive gravitational waves. So neutrinos, they are a great messenger. So they are electrically neutral. They are essentially massless. They are unobserved. They track nuclear processes, so they provide complementary information to gamma observations. So we know that hadronic process is going on. So they may be able to reveal the source of cosmic rays. The problem is that they are very difficult to detect. So the question is, how difficult is that? Well, here is a figure that shows you in some sense, the energy distribution of light, as well as cosmic rays just in one single plot. So what can make neutrinos? You have to take a very high energy cosmic ray, for example, a static cosmic ray. You take the most abundant targets, CMB photons, you smash those together, or rather proton hits the CMB, and this produces the neutrinos I was talking earlier. That means that as cosmic rays interact at high energies, somewhere around the GCK cutoff, they start producing EV energy neutrinos. We can compute the flux of the neutrinos because we know the cosmic ray flux and the CMB intensity. It turns out that you can do this calculation and you will figure out that you need approximately 1 cubic kilometer detector to see one event per year. Okay, so that good scale detector hopefully is IceCube. So this is what you will see if I transport you to a South Pole surface. It's one of where our computer centers are. The South Pole is actually quite an amazing place, and Antarctica is quite a large location. Here I show you the Antarctic continents compared to the continental US to scale, so you can see the relative sizes among them. We have, well, I'm not myself, but I guess I get this question, but some of our students do get to go there and do fun things and science there in Antarctica. The ASCI Observatory is not that laboratory I showed you earlier, it's not all of it, but rather it is a detector that's buried inside of the Antarctic glacier. It is buried approximately 1.5 kilometers below the Antarctic glacier surface, and it's comprised of an array of detectors that we have organized so that they span approximately 1 cubic kilometer. They're organized in strings, and each string is going to have 60 detectors per strings. The separation, so horizontal separation is going to be approximately 125 meters. And then within each strings, our sensors are going to be spaced around 20 meters apart. What is the fundamental unit of IceCube? It's going to be the digital optical module. That's going to be a PMT encapsulated in a pressure resistant vessel. That PMT is going to have its own data acquisition system incorporated and the ability to communicate to the nearby sensors along the string. Like I was saying earlier, we cannot see the invisible neutrinos, but we can see the particles that are produced by neutrino interaction. So for example, a neutrino can come through the planet, interact somewhere in the ice or the bedrock below the Antarctic glacier, make a muon. That muon is going to emit Cherenkov radiation in the ice, and we can see the light pattern of that Cherenkov cone. By looking at that light pattern, we can figure out the muon direction. We can also figure out the muon energy. So this is one of our event displays. So let me stop a second and explain you what you're looking here. The vertical lines are the chains of our experiments. They have little tiny dots on them, they're barely perceptible. And then you see that there are these balloons that have some color. Those are PMTs that have been struck by light. The color on the PMT or on the balloon tells you the time of observation. So red means earlier times and blue means later times. And then the size of the balloon tells you how much light was observed in each of these PMTs. So you can see here that the light deposition is not uniform. So if you measure the energy loss rate along the trajectory of the particle, it turns out that we're in a regime where the energy loss rate is proportional to the muon momentum. So by measuring the energy loss rate, we can infer the muon energy and from there infer the neutrino energy. These events are really big. This is one of our events overlaid on top of Boston Common, just south of the river. So far I've been showing you neutrinos, but when I was I mentioned neutrinos. So these are refinement diagrams of the charge current interaction that I showed you earlier. So the muon neutrinos we can see when they actually interact in the detector or when they interact around the detector and make a muon that goes through. Electron neutrinos we can see when they interact in the detector or in the borders around them, and tau neutrinos we are going to be able to identify when they're going to interact inside of the detector. And I will show you our first tau neutrino event later. These three Feynman diagrams map themselves into event morphologies within our PMTs. So charge-cube muon neutrino events are going to make these long depositions of light, which we call tracks. On those, because we do not know the initial muon interaction point, the inner resolution is very poor, within a factor of 2 approximately, but they are really good, well, comparatively good angular resolution, better than a degree. Neutral current and charge current electron neutrinos are going to make these blobs, which we call cascades. In this case, the energy is contained, so we can do a calorimetric measurement of the energy deposited, and our error on that is around 15%. However, now we don't have that long lever arm that we did in a track, so figuring out the direction is much more difficult. On our resolution is about 10 degrees at 100 degrees. Finally comes tau neutrinos, and tau neutrinos have this special morphology where, again, the colors means time, so red is earlier and green is later. So what you're seeing here is a tau neutrino interacts in the right point, produces a very boosted tau, and then tau decays. So this is known as a double cascade signature, and we can differentiate those around 100 dB and higher energies. Tau neutrinos are very special in neutrino physics because they are very hard to observe. And they're hard to observe for two reasons. The first reason is that because of the larger tau mass, the ratio of the tau neutrino cross-section to mu neutrino cross-section is suppressed. So most neutrino experiments operate at 10 GeVs. And in that energy range, the ratio of the charge current tau neutrino to mu neutrino cross-section is about 10%. So they are just difficult to produce because of that mass suppression. Additionally, they are difficult to identify because you're looking for that displacement between the production of the tau and the decay of the tau. The tau decay length is short, so in most typical experiments that operate on 10 GeV, that's going to be around half a millimeter. So the challenge here is to build an enormous detector that happens to have a good spatial resolution and also overcomes the suppression on the cross section. Luckily, in IceCube, we're going to have very high energy events, much higher energy than any accelerator-based neutrino experiments. So where are the neutrinos that IceCube observes coming from? Those neutrinos are predominantly going to come from cosmic ray air showers. And I was like mentioned earlier, a cosmic ray air shower, you're going to have a particle, say a proton, going to hit an air molecule and start a cascade of particles. The cascade of particles can produce pions, kaons, and other particles. Pions and kaons can decay, making neutrinos. Atmospheric neutrinos come from all directions. They're going to be a ubiquitous background for our searches. IceCube observes lots of atmospheric neutrinos on the rate of about 30,000 events per year. But we not only see atmospheric neutrinos. In the high energy part of our distribution, we also have an additional component that we think is associated, or we know is associated to astrophysical neutrinos. Most famously, we announced some years ago that we saw one of our high energy neutrinos in coincidence with a blazing gamma ray flare. That's known as the TXS observation. Okay, so that is more or less how IceCube works and why we built it. Now let me tell you, how do we use this detector to find astrophysical neutrinos? So the problem can be simplified in this video. What you're seeing here is 10 microseconds of IceCube simulated data. And you're seeing here is a bunch of particles is running down at your detector. So per year, we see 10 to the 11 muons. That's about 3,000 muons per second. And then we see 10 to the 5 neutrinos, mu neutrinos per year, and about 100 cosmic neutrinos per year. Okay. So the challenge is then to overcome that very high muon background and then additionally overcome that larger atmospheric neutrino background. So there are going to be 3 strategies to be able to do this. So the first strategy consists in just looking through the northern sky. In this case, I just look at the north, and in that case, the muons are blocked by the Earth. This then allows me to see only neutrinos, and then I'm able to see the artificial neutrino component as an excess of events in the highest energy part of the spectrum. So we have done that initially with 2 years where we found the first signatures, but now with approximately 10 years. What you see here in the plot on the left is you see a falling spectra of atmospheric neutrinos. Suddenly has a kink somewhere around 10 to the 5 GeV. That kink, we think, is associated with a superphysical neutrino signature that's compatible with a power law distribution of eta minus 2.37. This is a plot that shows you the same information, but just the infinite neutrino fluxes. And like I was saying earlier, a power law distribution looks about right for this. Okay, now let me tell you the second method. The second method is, instead of using the Earth as a shield, to use the pieces around the detector as a shield. And in this case, we're going to have access to all sky vision, because now I can look at the southern sky, but the downside is that I'm going to have a smaller detector. So if I look at the distribution of events along 2 axes, on the left axis, I have the number of photoelectrons that an event deposited inside of the detector. And in the right axis is how many photoelectrons are deposited in the outer part of the detector. The vertical scale here is a 3-dimensional histogram. So you can see that there is this large muon background that's just continuously falling down, leaving high energy events that also have high energy charged position on the Beetle region. However, you will notice that there is an additional component that appears that is not connected to this falling background. That component is associated to very high energy events that leave essentially no charge in the Beetle layer. Those are going to be within astrophysical neutrinos. That selection has actually observed some of the highest energy astrophysical neutrino we have measured. The first one we saw, we decided to name after Muppets. Now we have seen many more, so we just named them with a little more boring names. Using the high energy event selection, you can also measure astrophysical neutrino spectra, and that spectra turns out to be something around eta minus 2.9, and it's also good feature data. I want to point out that I was telling you earlier that we measure a spectra also with northern track muons, and that spectra is quite distinct than this one. And we'll go back to that point in some minutes. Now let me tell you the third way of doing it, and it's by finding tau neutrinos. So in cosmic air showers, you predominantly produce pions and kaons as the mesons that yield most of the neutrinos. Pions are going to dominate the lower energy neutrino flux, and the higher energy neutrino flux that's relevant for astrophysical neutrinos is going to be dominated by kaons. There is also a possibility, so neither kaons or pions can produce taus just because they are not massive enough. However, you can also have the possibility of producing higher mass mesons, in particular charm mesons, like the D meson, could produce tau neutrinos. However, the production of tau mesons in the atmosphere is extremely small. That means that if I start seeing a large amount of tau neutrinos, or comparatively large amount of tau neutrinos, that must be astrophysical neutrinos. So how do we see tau neutrinos in general? So how we do it is by looking at the kink that separates the production of the tau with the decay of the tau. These are just 2 examples from the Donald experiment at Fermilab and the Opera experiment in Italy. In these experiments, you can see the axis, the separation that you're looking for is of order of millimeters. In our case, the separation we're going to be looking for is much higher. Our neutrinos are going to be PV energies. Just to give you a sense of scale, if you have 1 PV neutrino, that's going to go about 50 meters. We actually found one of these neutrinos, this analysis that I did a couple of years ago with some of my IceCube friends, and we found this event that's quite interesting. This event deposited 90 TeVs of energy in the detector. We think that we identify it has a first and second bang. So what you want to see here is the panels that border the event display, and in particular the panel with the arrows on the right. So each of these panels shows you the charge deposition or the number of photons as a function of time in each of these detectors. So what you can see there is that in multiple of these panels, you see the first light deposition followed by second large deposition. So the first light deposition, which is the largest one in that peak in red, is the production of the tau, and the second one is the decay of the tau. This tau, we think, going around 70 meters, which is a lot. So using these three techniques, we have been able to measure the astrophysical diffuse spectra. So it's shown here in comparison with the gamma rays measurement by Fermi and the cosmic ray measurements by Oyer. And they're shown, the red band in the center shows you the measurements we have from northern tracks measurements that gave you that e to the minus 2.3 spectra. And then there's a measurement from starting events shown in pink. You will notice by looking at the pink and red that if you just extrapolate that red line to lower energies, that doesn't seem to be able to explain those two pink data points. That is the reason actually why the spectra measured in the starting events, the pink one, is much softer. Okay. So what is that indicating? So we know that if you think that neutrinos are produced in conjunction with through a pion production process, if you're producing charged pions, you produce neutral pions, so there should be some gamma ray production. So currently, the models that are able to explain the neutrino data sets that go to lower energies, that means to go down a little below 100 TeVs, are essentially saturating the Fermi diffuse measurements. So you can see that in the plot on the right. So the blue line is, the blue region is a scenario where you produce the neutrinos to a proton gamma interaction. And so that line matches very nicely the neutrino data. That same model then produces pions, and those pions predicted by that model end up in the red. So that seems to be saturating that Fermi data set. However, if you then make the neutrino spectra keep going at lower energies, you can extrapolate this, and you will imagine that the neutrino or the associated gamma ray flags could be overshooting the Fermi data. So there are some hints in our data sets that do indicate that at lower, as we go down in energy, the spectra continues and becomes steep. We have also looked for neutrinos through what we call point source analysis, and this is one of our latest results using 10 years of IceCube data. We have a hotspot in the northern hemisphere, so you have in a minute, and we have also an additional set of sources. So the hotspot that we have found in the northern hemisphere is NGC 1068, and it has been it's been the most significant source that we found in our state search. So as you probably know, NGC 1068 is a Cypher galaxy with a heavily obscure nucleus. Let me just show you the result. So this is our measurement of the neutrino spectra shown here. So for the neutrinos that we associate with this particular source, we get a spectrum of order e to the minus 3.2. Takeaway so far is that IceCube can see all flavors, and that's particularly important to distinguish astrophysical neutrinos. For example, the tau scenario. We have measured the diffuse astrophysical neutrino flags with both these cascades and track morphologies. There is some discrepancy in the results that you obtain by a simple single power loss between different observables, and that seems to be associated with a steepening of the low energy flags. The soft diffuse flags hints to our gamma opaque neutrino sources. And we're also excited that we are starting to see first neutrino sources appearing. So let me switch gears a little bit and tell you about some particle physics measurements that we can do with those neutrinos. So one thing that was announced in Nature recently is the observation of what we call the glacial resonance. So the glacial resonance is an interaction of an electron antineutrino with an atomic electron. And that interaction happens in the lab frame where the electron is at rest, and it produces a real W. The energy needed to have that resonant production of a real W occur it's close to 6.3 PeVs. So it cannot be produced by any anthropogenically made neutrino beam. We have seen an event whose energy deposited on infer in our detector is extremely close to the energy expected by the production of a W. This event was not contained in our detector. You can see the event figures in the bottom. And so the left plot shows you the event interaction vertex that was just on the side of the detector. So how do we know that this is a real W production and not just a very strange muon that happened to have a very large loss that skimmed through the detector? As you remember earlier, the detector is being ran by muons, so strange muon losses can happen. So there's going to be a difference between the hadronic interaction and an electromagnetic interaction produced by a true-going muon. In the hadronic interaction, you're going to have a production of muons from pion decays, from pions producing the hadronic shower. That is not going to be, or that's going to be lesser the case for the case of an electromagnetic shower. So what that implies is that when you see a shower develop, if you have an hadronic shower, there's going to be a muon component along the boost direction of the interaction that's going to stick out because those muons are going to go at the speed of light, whereas the electromagnetic shower is developing at a slower speed. And that's exactly what we see in this event. The event is sort of cartoonishly shown in the top. We see the event approaching, and then we see that there are some first initial hits before the actual event's main shower hits the detector. We identify that those hits are consistent with early muons produced by pion decays. Okay. So now let me talk about in that same line about things you can do with the high energy neutrinos. One thing that you can study in not only in IceCube but in other detectors is dark matter annihilation to neutrinos. This is the idea here is that you have dark matter particles that annihilate into standard model particles. You can pick your favorite theory to pick how do they annihilate the standard model particles. And then those standard model particles can decay into stable products. For example, neutrinos, gamma rays, electrons, and protons. And then the game is to try to look for excess of the stable particles in regions that we know have large dark matter density. So we have done analysis using the highest energy neutrinos I showed you earlier, looking for excess of events around the electric center. So how does that look? You can see that in the plot on the left, where I show you our high energy events, shown as crosses here. Those are events above 60 TeVs. Overlay on that, you see the excess we will expect if there be dark matter annihilation into neutrinos. So that's going to yield, well, unfortunately for us, it yields actually a constraint, so we don't see a significant excess of events. And we can put a constraint on the annihilation of dark matter into standard model particles. These constraints are going to be complementary to constraints that you can put using gamma rays and other detectors. That actually can be done not only with IceCube, it can be done with essentially any neutrino observatory. So this is a review that I brought recently with the people shown below that shows you how, as a function of the dark matter mass, you are able to constrain the annihilation cross-section all the way from MeV scales to PeV scales dark matter. But there is something that is uniquely enabled by having a high energy neutrino source, and that is the following idea. So we know that, or we have seen that the Neutrino Sky, or the most of the neutrino sources, are produced by extragalactic neutrino sources, or that's what's dominating the diffuse neutrino contribution. That flux is going to imply or consist in an approximately isotropic incoming flux of neutrinos to us. If there is an interaction between neutrinos and dark matter, and that interaction is sizable, what could happen is that if you have neutrinos that are going through the electric center where the dark matter density is highest, those will get attenuated compared to neutrinos that are actually coming not from the galactic center, but just directly to the Earth. And so the idea here is that the neutrinos are acting now as a beam, and the dark matter is going to be targets in our laboratory frame. And the interaction between dark matter and neutrinos is going to produce an anisotropic signature in the neutrino sky. So let me show you how that sky looks again. So here are the high energy neutrino events that I was talking earlier. That's starting event selection. You see them overlaid on top of the column density of dark matter. It will seem from this figure, which is actually an axiom, we seem from this figure that there is less neutrinos around the galactic center. But I swear you, if you actually do a statistical analysis of the distribution of these crosses and excesses on this event, you will find that the sky map that you're seeing here is compatible with an isotropic distribution. So that actually constrains the amount of anisotropy that we allow in the neutrino sky. The interaction between neutrinos and dark matter not only produces an anisotropy in the neutrino sky, namely that you expect less neutrinos around the galactic center, but it also is going to imply different effects in the energy distribution of the neutrinos that are going to come to us. So I'm just going to give you two examples that we study here. So in one case, you're going to have scalar dark matter with a fermionic mediator. That's the left case. And in the right case, it's going to be a fermionic dark matter with a vector mediator. And the thing that's interesting is that, for example, in the left case, you're going to have this S-diagram process, or S-channel process, sorry. And that S-channel process is going to enable a resonant shape in the cross-section. And what that's going to do, it's going to actually deplete the neutrinos at a particular energy. On the other hand, if you have the vector-like interaction on the right, then the way that the neutrinos disappear is going to be different. So this analysis is not only a study of anisotropy in the neutrino sky, but it's a study also of the energy distributions of the neutrinos as well. So with that, we can place constraint into these into these observables. Let me just talk about the plot on the left, because these plots are rather busy. So the horizontal axis on the plot on the left is the dark matter mass, and the vertical axis is the mediator mass of the process that you see in the left. And the color scale, what the color scale tells you is the maximum size of the coupling that is allowed for that process. And so to understand how competitive these constraints are is we should compare them to cosmological constraints on dark matter neutrino interactions. So the pink line that I have drawn here shows you the regions where the ASCI constraints, by looking at anisotropy of the neutrino sky, are the dominant constraints, and where cosmology actually gives you the most relevant constraints. Okay. So IceCube actually is going to bring new capabilities to understanding dark matter. Now we can actually look at essentially, in some sense, what we're doing is inverse direct detection experiments, where now the dark matter is just sitting still. The constraints we're getting on neutrino dark matter interactions are competitive with cosmology, and those are going to just get better as more data comes through. Now let me tell you about the second example, and I think the second example is interesting because it emphasizes how neutrinos are natural interferometers that can prove extremely small scales. So as I was saying earlier in my talk, neutrinos change flavors. So they have a natural sense of time that allows them to change from an electron neutrino to a mu neutrino and back and forth and back and forth. If you do anything to mess up the internal clock of the neutrino, that will change the way the neutrinos transform between one flavor to another flavor. So if there is anything along the way from the neutrino production to neutrino detection that can do that, you will be able to pick it up. And I'm going to focus this discussion in terms of Lorentz variation, but this is extendable to other things. And in some sense, what we're trying to do here is very similar to Michelson-Morley's measurement or interferometric idea of looking for ether. What we're going to try to do here is use the internal clock inside of my neutrino to see if there is anything along its path that interferes with that clock and allows us to see it. And so for that, I'm going to use the flavor composition of astrophysical neutrinos. And we organize them typically in 3 categories. So we have neutrinos from pion decay, which produce 1 electron neutrinos and 2 muon neutrinos, which we call a 1 to 0 source. Then we have neutrinos from neutrinos producing sources that could have large magnetic fields. In that case, the muon will lose energy before actually decaying into neutrinos, and that sources will only produce as muon neutrinos of high energy. So we label those sources as 0, 1 sources. Finally, we can have neutron production and neutrons decay yielding electron neutrinos only. So these are actually sort of toy scenarios. In the real sources, of course, you have a combination of these channels. So we like to talk about the flavor astrophysical neutrinos via the flavor triangle, and this can be a slightly complicated plot to look at. So let me explain you how to read this plot now. The horizontal axis tells you the fraction of electron neutrino at Earth. The right axis tells you the fraction of muon neutrino at Earth, and the left axis tells you the fraction of tau neutrino at Earth. If you have a point up there in the top, that means you have 100% muon neutrino. If you have a point here to the right, it means you have 100% electron neutrino. And if you have a point to the left, that means you have 100% tau neutrino. If you are somewhere in the middle of the triangle, you go along the directions of the numbers, and the conventions in all these plots are always the same. You go along that horizontally to the muon, and then diagonally as shown here for the tau and electron components. In this particular case I show you here, this is equal contributions of the 3 flavors. So if you know the different neutrino sources, you can actually predict what's expected flavor composition at Earth. So here the different sources are given by different colors. And given the uncertainty on the flavor on the mixing parameters of the neutrinos, you have actually that the initial flavor composition spans a sizable part of the space. What is important here, and you should note, is that most of the triangle is white. And that means that if you find a flavor composition inside of those white space, those cannot be produced by any type of these sources. And if you look at linear combinations of any possible source, you will always end up somewhere in the center of this space. So now we can go back and use that tau neutrino measurements I was telling you earlier. And this result of our flavor fields are shown on the right. The result is the black line, and the sensitivity of expected is the green line. This analysis uses the 3 morphologies that I was talking earlier, the tracks, the cascades, and the double cascades. So the first important point here is that the flavor composition of astrophysical neutrinos is compatible to an equal flavor. So the center part of the triangle is definitely allowed and preferred. The limits are actually quite weak. Most of the triangle, in fact, is allowed at 95% confidence level. But the corners of the triangle are not permitted. So some part of phase space is being constrained. So how does that go back to my idea of trying to constrain Lorentz violation? Is an idea here is that there is some remanent field. The Lorentz symmetry is not exact, but there is a remanent part of it that remains in space. And that Lorentz violating fields could be interacting with the neutrinos. Again, what you should think about here is like a Michelson-Morley interferometer where you're trying to see the effect of ether. So that actually is going to do interesting things to the flavor triangle. So the plot on the right, which looks like a metra map, shows you how different ways of introducing the interaction between the neutrinos and this Lorentz violating potential modifies the flavor expectations. So for example, yes, let me pick one of these to exemplify. If I pick the yellow one, that means BE. So if the Lorentz violating term operator acts on electron neutrinos, and you start with a muon neutrino being, so that means like no electrons only muons and notals, then you go from the red point to the white point. So the standard model starting points are shown as black, and the white dots is where you end up if you have Lorentz violation. So you see that most of these trajectories are inside the parameter space. However, some of these cases lead you to these corners, which we know is just impossible. So you can translate that into constraints of the strength of interaction with Lorentz violating fields. And these constraints are going to depend on the source flavor composition, which is shown in the horizontal axis. And I show them in terms of the Planck scale square, because that's the natural scale to compare in this problem. So what's interesting is that this interferometric technique can have Planck scale sensitivity. However, it has large dependency on the initial flavor composition of the source, which is something that we need to resolve if we want to claim that we have seen or not seen these sort of effects. So the takeoff here is that astrophysical neutrinos, just because of the long lever arm, are able to do these interferometric measurements and can have sensitivity to extremely tiny effects, such as effects expected from gap theories that are suppressed by the Planck scale. So in the last minutes that I have, I will just talk about the future. First, I hope that I convinced you that IceCube can do a plethora of things. We can do particle physics, we can do astrophysics, and that follow the discoveries we've done in the past, that we can still make new and increasingly exciting new and exciting observations. And I see that because IceCube is going to keep growing. So we're going to grow in 2 stages. So the first stage is called the IceCube upgrade, and that's installation of 7 new additional strings in the center of the detector. You can see that on the figure here. So the blue are the current IceCube strings. The green are some inner parallel data called deep core, and the red is the innermost detectors that we would like to deploy in the next years. This is particularly important because this new detector allows for better reconstruction of energy and also better reconstruction of flavor identification. So we'll increase our capacities to consider the flavor triangle I was showing you earlier. Then later part of this decade, we hope to construct something known as the IceCube Gen 2. And so here you can see in red, the current IceCube array, and in green and blue, you can see the deep core and the proposed or the to be built IceCube upgrade. The IceCube Gen 2 second generation is going to be 10 times larger in volume than the current detector, and we hope that that will give us significant increased sensitivity. This is just a handful of experiments, or these are just how the IceCube experiment is going to move forward. But there are other experiments that are going to come online. I'm particularly fond to this idea called Tambo, which is an idea proposed to be built in Peru. And the idea here is to look at the mountain, essentially, and look for neutrino interactions inside the mountain. So if you have a tau neutrino that interacts inside the mountain, at the tau is able to escape the mountain material, and it can decay in air. So if you put detectors on the other side of the mountain, you can then see this tau decay. So essentially, what you're trying to do here is just trying to stare at a solid wall of rock, and you're trying to see if a shower comes out of it. And if it does come out of it, then that they have seen a neutrino. This technique has been done in other experiments, but this particular setting here has quite nice geometry. That's not the only case. And so here I show you a summary of what is going to happen in both neutrino physics, the particle physics, and the neutrino astrophysics. So the important thing here is to look at the top box of the left plot. That shows you the volume of neutrino telescopes. So right now we have only IceCube working. So that's about 1 cubic kilometer. But soon we'll have Baikal in Russia and KM in the Mediterranean that are going to be operating. So in a couple of years, the effective neutrino volume of the Earth's telescope is going to be somewhere around the 5 kilometers cubed. Later, next decades, in the 2030s, we hope that the IceCube Gen 2 will start. That'll be a great improvement in effective volume that will actually add to the current, to the ongoing experiments. So between now and the 2030s, in the 10 decades, we expect to have 15 times more total neutrino volume. to see these neutrinos. And like I try to emphasize, neutrino physics is also going to move forward through terrestrial neutrino experiments. And here is some of them. Those terrestrial neutrino experiments are going to make precision measurements of neutrino properties and interactions. And so these two efforts are synergic one to another. And so I show you what we hope will happen if we could be in 2040 when all this has already been constructed, hopefully. So this is the flavor triangle that we hope to see in 20 years from now. The smallest of the circles is the combination of all of the telescopes. And you can see here now there's different color regions which corresponded to different production models of neutrinos, or flavor models of the neutrino sources can now be differentiated. For example, definitely like we could tell if a source is producing neutrinos through neutron or muon up and pion sources. So with that, I think we live in really exciting time for particle astrophysics. First, sufficient neutrino sources are appearing. Diffuse neutrino measurements hint towards gamma-opaque sources. High neutrinos give us a new way to search for dark matter. And neutrino interferometry is a powerful tool to see new effects. And I think that is growth continues in the future. And major physics VVSM. And thank you.
Thank you so much, Carlos. So please join me in virtually thanking Carlos for his great talk. We have some time for questions. So if you want to ask a question, please use the raise hand feature. Charles?
This may actually turn out to be a rather silly question, but I'm just wondering, do you have any sensitivity to additional flavors of neutrinos? Like if there was a fourth flavor in your data, how would you see it, or would you see it?
Oh, that's a great question. I love that question because I'm always also hunting for new neutrino flavors. Yeah, so if there are new neutrino flavors, typically those new flavors don't, it depends how you introduce the new neutrino flavor. Normally, if they are light, so below the C mass, in the neutrino mass is below the C mass, then they could not participate in the standard model interactions, as far as we know. So they will just become invisible. So what you would see is a deficit of neutrinos of that in some particular energy dependence on so. So that would be very tricky to disentangle from the normalization of the flux. If you are not heavy, neutrino is very heavy, so it's able to produce signatures. Then yes, you could see some things, but it's essentially very model dependent. I'm not sure to answer your question. Sorry, it was a little. It's a very complicated answer because it depends on what we mean by a four neutrino flavor.
Mm-hmm. Okay, thank you.
Thank you for your question.
You have another question? Thank you, Giovanni.
Yes. Can you contribute anything to the measurement of the neutrino masses?
Yeah, so the answer is in short, no. I think the closest we could do there, with the neutrino masses, the absolute neutrino mass, no, I don't think so. No, that doesn't work here. The lowest energy neutrinos that IceCube could see, which is the ones that are more relevant for the neutrino mass problem, are neutrinos producing supernova. And there, how we observe those neutrinos is that when if a galactic supernova happens, you have a huge wave of neutrinos. So because our detector is one of the largest, we can measure the time emittance of the supernova very well. That gives information about the neutrino parameters and orderings by observing those MEV neutrinos, but I don't think that gives you the neutrino mass, unfortunately. So that is typically, no, I don't think you can do it with this.
Okay, thank you, great. Yeah.
I'm gonna use my prerogative as the host to ask you a question related to this. If there was another 1987A tomorrow, like another galactic-ish supernovae, how many neutrinos would you expect to see? Like, what would you learn about supernovae from this?
Yeah, that's really a cool question. So we will learn a lot. We will have to, switch gears completely to see what's going on for at least a couple of years because it's going to be so much information. So like I was saying, we only measure the time distribution. That could help the neutrino ordering, for example. If the neutrino mass ordering there, we know that 3 neutrinos, but we don't know if they go 1, 2, 3 or a different neutrino mass order. So you will be able to figure that out very, very quickly. Also, the directionality of the supernova with neutrinos could be figured out as well, just because it's a plane wave that's going through your detector. So you can use that to infer the direction of the plane wave. I think hyper K is probably also really good at telling the direction of the supernova with neutrinos. Because they can look for electron neutrino scattering that has very good directional information. But after hyper K, probably IceCube is the second contributor to the directionality of the neutrino supernova. Then, of course, you could also do things like, neutrinos have extra, can decay, for example, or unstables. You could also certainly improve that. There were many fundamental neutrino parameters that are still very, like the charge or the lifetime, that were neutrinos for supernova 1987 are still providing the strongest constraints. So you will be able to do those sort of tests.
Very cool. Thanks. I think Charles has another question.
Yeah, I wondered if you'd be willing to make in some sense, an editorial comment on the relative merits of the technologies. So you're clearly vested in IceCube, but what does Baikal have any advantages over IceCube, for instance?
Yeah, good question. So more neutrinos is better. Neutrinos are essentially statistically limited, especially statistical neutrinos, statistically limited problem. So we need more neutrinos from everywhere. So Baikal has been doing really well in the ability that they have to construct their detector. And the reason is that the deployment in Lake Baikal is more manageable, because what they do is when it's winter, they go on top of the frozen lake, and then they can deploy their detectors by drilling, and then they go back to the shore, which is something that's not possible, or it's much more difficult in the Mediterranean, and it's of course also difficult in the South Pole. So Baikal has the deployment advantage in terms of putting out more sensors. They can also, because of the same reasons, they can rearrange their strings fairly easily. Well, it's not trivial, but they could do that so that they could then adjust their configuration to optimize for different energy ranges, because the separation of your strings determines what your optimal energy is you're shooting for. So that's, I think the water detectors have that capability. Water detectors also have an improved directional resolution. So that is going to help in terms of pointing, of finding neutrino sources. So that's what I would say. I think they're very complementary. And in ice, the advantage is that the ice is more transparent than the water. So that means that for less money, we can build bigger effective volume, but the quality of the events is maybe a little poorer just because of the additional scattering. So the events that they're going to see in the ChemTreeNet probably are supposed, we will see how they turns out to be with systematics and so, but the idea is that the resolution, angular resolution is supposed to be better. One thing that's not in this plot that I show here is the radio experiments. That's another way of finding neutrinos, but in that case, the energy threshold is very high. And so we expect that especially for GCK neutrinos. Does that answer your question?
It does, thank you very much.
Thanks for your
question. That's we're a little bit over the hour. So if there are any last questions, please ask now. Otherwise, let's thank Carlos again for a great talk and for coming virtually visiting us. And yeah, he's around, so please reach out to him if you're interested. Thank you all for coming.
Thank you. See you soon.
Thank you.
Bye.
Thank you so much.